So what remains from the part one is very interesting. Last Sunday, yesterday. Yesterday, there is a student asked me one question over the, hey, what is the problem if his program has a malloc and a malloc, no matter what the size or it's just returns an points. Okay, so it's because you don't understand what is malloc. Okay, if you understand malloc, then you understand that it's your fault. Okay, now I will tell you today what exactly is malloc. Okay, so malloc is a very naughty guy. Okay, first of all, malloc, you have experienced something like this. You call malloc, you know that you allocate 10 bytes, but you accidentally write over 10 bytes. Sometimes you have segmentation faults, sometimes won't. Yeah, I mean really sometimes, okay? Sometimes has, sometimes don't has, and it totally depends on whether you execute a program, or some people even complain to me that they get segmentation fault because they call free. Once they call free, they get segmentation faults, and they then develop a habit that never call free. Okay, and what a nice excuse. Okay, yeah, but yeah, I will tell you today what happened inside malloc. Okay, so what exactly this? I can click it. Okay, so what exactly is this guy? This guy is this paint part, okay? Paint or red, it doesn't matter, okay? So this part is actually a wide area. How big is this? Let's say this is a 4 gigabyte accessible memory, so that means a 32-bit CPU. Usually that area is composed of a memory of 2 point something gigabyte. Okay, really huge, huh? So how about 64 bits? I don't know how to count. It's basically 2 to the power 64 minus 1G. Particularly, the 1G is usually from the kernel. Okay, so it's a huge area. So this drawing is not drawn to scale. Okay, this area is huge. Now, why I say it's huge? First of all, it is something that is really for your allocation. So you have two status: either it's unallocated or allocated. So once allocated, that means that you call malloc. You create a piece of memory here, which is for your program to use. Okay, so a piece of memory. I know where it is. Okay, it's unallocated. That means that once you touch it, read, write both generates segmentation faults. Okay, it is unallocated. Once it's allocated, you can touch, you can read, you can write. Okay, once you go beyond that barrier, what is the barrier? Later on, I will tell you. And cross some barrier, then you will have segmentation faults. Okay. So, first of all, you know what's dynamic, right? You can grow the size. Okay, how many of you have called a function called valloc? No one heard of it? No one. Really? Valloc. Yeah, it's of a family of malloc. No one knows this. Now, how many of you knows all 4 cores? 2? Two. You know 2, right? Which 2? The malloc and free, huh? So how about this guy? This guy is yeah, you can read the manual. It's just with different malloc parameters. Just they use how many numbers of members and the size. They just do multiplication. It doesn't matter. Just the malloc variations. Valloc is something special. It allows you to reallocate something which is already allocated. So you allocate a piece of memory of 10 bytes. Now you think that 10 bytes is not enough. Make it 1G, no problem. Yeah, just tell me that, yeah, I give you back a pointer, okay? You recreate that piece of memory into a bigger range, which is 1G, okay? So this is valloc. So based on this behavior from a programmer point of view, you already understand, yeah, which is really dynamic, okay? Is based on your request, is on demand area. So on-demand area is based on allocation. Before any allocation is unallocated, and sometimes you will heard of this kind of explanation over malloc and free. So what is that? Usually when the first time you heard of malloc, so what is malloc? People will tell you, a function that allocates memory for you, right? There's something people will try to give you a brief idea over malloc, and the free is a deallocate, right? To deallocate the memory that's returned by malloc, okay? And in this part, in this 1 hour lecture, you will understand that these 2 sentences are all wrong, okay? Both are wrong. And I don't mean totally wrong, partially wrong, Okay, what's the meaning of partially wrong? It means this area, the LK memory, may sometimes don't allocate. Yeah, they just try to doing some recycle thing, recycling some old memory, recycling some previously unallocated memory. So that means on the other hand, this 3 again is partially wrong. It's not always the LK memory. I don't know whether you have tried. You have some box, okay? The box is like that. You malloc memory doing some processing and free it, but you accidentally try to access the LK memory. Okay? You call free and try to read it. You try to write it, still works. How many of you have tried this? Yeah, usually the bug is because you accidentally add a free there. Okay? Suppose that you have to delete it. Okay? If you have tried this, that means that this sentence is kind of a wrong statement, right? So both of them are wrong. I can tell you, I'm very sure I can write a program demonstrating this totally wrong. Okay? And why is wrong? It's not because the malloc and free just imagine to produce something which is unpredictable. It's always be predictable. Okay, we can predict what exactly the memory address, not exactly means kind of exactly the memory address that we will allocate, whether we will generate a new piece of memory or which is not allocating because of we call the malloc, not deallocate because we call free. We know how. Okay, so basically you are going to hear and listen to me how to generate corrupted memory, how to corrupt memory, and why you will corrupt memory. All right, let's go. So malloc and free together is actually controlling one very simple things. Okay, I know that some people have asked me, hey, you know assembly, okay, CPU, okay, which is a really small CPU. It's just a frame pointer, stack pointer to control something. The heap is very similar. There is a unallocated area by start, okay, which is a free heap, no one there, okay, and once you touch the heap memory, you will generate some application for, I'm sure, okay. Now after you call malloc, okay, so basically what is the meaning of malloc is to grow, okay, just like water level. This is water level. This is water tank. Okay, you want something more? Okay, I raise this bar. Okay, and this bar have a name. Okay, some very old book we call it a brick. Memory brick, okay, B-R-E-A-K, brick, okay? This brick, okay, will grow so that you cross the brick line, you will have attention points, whether you go read and write, okay? But if you're within the allocated memory, still good, okay? You can read and write those allocated memory. So this is the raising of the water level, and you can change the water level by calling free. So malloc will grow it, free will change it. Okay. Now the problem is, well, we only have one brick line. Okay. So what is your line? And let's say you have one brick line. Okay. How about I grow it whenever there is a malloc call? I grow it by that exact amount. And someone try to free some old memory. Can I change it? Or how much I grow? Let's say every time people ask for some memory, I just grow it to 1 GB. Okay, I don't know whether you know it. Java VM is doing this. Java JVM is doing this. Whenever there's a new program running, it just grow the heap size by 2 GB. Okay, and it's just a pretend that yeah, I have memory. Please take it. Okay, so this is not controlled by you. And if you want to control it, usually you will use this kind of program, right? The malloc call. Now I will demonstrate something horrible to you. So what is the horrible things? The horrible things is, first of all, how many of you don't know that malloc return an address? Okay, everybody know, huh? If you don't know that, I don't know whether you can drop this course, okay? Yeah, that means that your assembly 1 and 2 not using malloc. Okay, so it's return your address. Now what is that address? I want to compare their distance. So what is the meaning of compare distance? I just save it in point of 1 and point of 2 and do a subtraction. Okay? So I will use the char pointer so that it is byte addressable. Every piece of elements, okay, in that memory is addressed by bytes. Okay? So whenever I do a subtraction, that means it return me exactly how many bytes between them. Okay? So per core, it is 16 byte. So you will expect that pointer 1 and pointer 2, pointer 1, let's say it starts with 0, okay, 0 is a magic number, okay, or 8. Then pointer 2 must start with maybe 8 plus 16. Let's see whether it is true or not. Okay, this is the program. Okay, so I'll compile the program. What is the name? Malloc distance. Okay. First of all, let's you take a look at malloc distance. Okay, so at this time I even make it 3 trunk. Okay, so the 3 trunk 1, 2, 3 allocated sequentially. Okay, no, in the middle there is no other malloc call. Okay, so I have 2 minus 1 and 3 minus 2. Let's go. No problem. Maybe I show you warning as well. Even warning is no. Okay. Let's go. What can you say about this? Does it mean that wow, great, malloc actually is a friendly call? Okay, it's not that I'm so stupid that I will write over it. Okay, so generating it request for 16, right? It gives you 24. Okay, well maybe you don't trust me. Let's try something bigger. Let's try something bigger. What's the number that you want? 1K lah. Okay. Yeah. Too big. 1K. 1K. What happened to my fingers? Okay. 1K. All right. Compile. Run. Oh, by the way, how many extra bytes are given? 8. How about previous example? 8. So that means that it's not something random. It's hard code, right? Every time malloc gives you memory, and in between 2 trunks of memory, there is an 8 byte. Now, there's one more thing. Very important. The malloc call, the 3 times malloc call is actually sequential, right? What does it mean? You have malloc call 1, generate memory, and next to it will be another malloc call memory. Next to it is another one. It's not separated far away. They are just close together, and it is illustrated with this diagram. Okay? So the first call, you generate 16 byte, but before it, there is a data structure actually. It's governed by the GNUC library. The GNUC library asks for extra slot, okay? And this slot, I call it just a data structure. Actually, this is a linked list, okay? And what's the next? Next is your second call. Your second call will generate exactly the same pattern. There is a data structure before the memory that you can use. So the distance between them, I do a subtraction from this address to this address. So the difference is 24. So that means it's telling me that in between it, the data structure costs 8 bytes. Okay, there is data structure in between it. Okay, and there is one funny thing. The funny thing is what? If you're using pointer 1, start writing memory, then write data to the memory. Actually, you can cross the border and pollute an other malloc call. Understand what I mean? Do you want me to try? Okay. Yeah. You know, I'm just a monster. Okay, always damage things. Okay. Yeah, just to reset it. Okay, so make it back to 16. Okay, I know what you are going to do. You want me to do this. For I equal to 0, I smaller than how many? Maybe 16 times 3. Okay, I plus plus. Okay, and let's say pointer 1. Because it's a pointer, you can dereference it. Okay, treat it as an array, right? You start with the first log and then dereference, and just like an array. So next logs is PTR1, PTR2, PTR3. So it's actually that I'm going to write through the free malloc area. I just forget about the 8 bytes extra allocation. Okay, I just try to do this and set it equal to I. So we expect that every byte will be different. The first byte is 0, and then 1, 2, 3, 4, 5. Okay. So what can you say when I do this? What is the value? Can you predict it? Is it 24? Let's go. I predict it's 24. Don't make it. Okay. CSCI. Okay, so because I didn't use pointer 3. Okay. So I have a clear look again. This is the program. 24. Yes. Yeah, at least I'm as good as a primary student. I can count. So what can you say about this? What can you say about this? From the first year you learn C, someone tell you malloc, until now, actually you are not understanding malloc. Yesterday I follow up the Facebook reply. I tell him it pollute the memory. Actually, he don't understand what is the meaning of pollute. What is the pollution? The pollution is all because of this map. All because of this map. This map tells you that malloc is generating a piece of continuous range. Right. I can start writing from this address all the way go down to pollute other areas. No problem. And I can even predict how I pollute it. Because I know there is a gap between it, which is 8 bytes. So previously, I tell you that I can predict exactly what is the damage is true. Because I can always predict what is in between. And then I know what are the number of cores and what is the size of it. And then I can predict exactly what is the damage. And now this is the only level 1 damage with level 2. Level 1 damage is, here, I cross the border and pollute another guys. Maybe another guys welcome me to pollute him. Yeah, it's stupid, right? But yeah. The pointer 2 will welcome me to pollute. So this is level 1 damage, pollution over the memory that is being allocated. Second layer pollution. Second layer pollution is really stupid, huh? What happens if I do this? Yeah, I try to free some memory. Okay. Actually, I don't know what will happen. Maybe I try to free them all. Okay, free pointer 1, pointer 2, pointer 3. Okay. Yes, let's go. First lecture to take a look at the program. A little bit different. Okay. CSCI, no problem. Yes. Second layer pollution. What is second layer pollution? Take a look. What is the error? It just pop out. It's not something that I generated, right? It's that I made the error message. Error message is not generated by me. Who generated the error message is just something that hard code inside GNUC library. The GNUC library thinks that you are doing something wrong. What's the thing that you are doing wrong? Is while you are doing free, invent the next size. What is that? What is that? It's because you pollute the data structure in between. The data structure, we call it management block. Okay, the malloc code manage its own way to generate the malloc sequence. Okay, you pollute it and try to even make use of it and tell it, yeah, I know that I want to free. Okay, please look up the memory inside your management block and manage your free memory. So something bad happened. Okay, I don't know which core it is. I just predict. Okay, I predict it's the second free core generated error. So let's locate it. Pointer 1. Okay, pointer 2, pointer 3. I predict that the second core generate the error. So if it is the first core generated error, you won't see PTR. You will see PTR1 and won't see PTR2. If it is second free core generator error, it will show PTR1 and PTR2. so on and so forth. Okay? Whoa. Let's get it. CSCI. Okay. Oh, sorry, it's first call. Yes, it's totally corrupted. Okay, it's just trying to look up the next block. All right. So yeah, I got it wrong. But wow, what can you say about this? What can you say about this? It means that the malloc is not just give you a piece of memory. It's not that simple. It's not that simple. Okay. So so I will continue to talk about the free call first of all. Okay, I didn't explain what is a free call, right? So that you don't understand what is going on previously. So the free call is actually doing this. It is doing the shake, right? Doing the shake. Now let's say I'm having this allocation pattern. The allocation pattern has 4 blocks. Okay, I never called free before, and this is the first time I call free. The guy who is the victim, the last or the biggest pointer, biggest address for the last guy, then I want to deallocate. Now, deallocate the last guy is easy, always easy. How easy it is? Just from this old heap to this new heap, shank it, right? Easy. You understand what the shank? The shank that, let's say, is water level. Is water level. There's a tube of memory here. You raise and rise the water level to guarantee how much memory you have. Now, this is the last guy that I want to deallocate. Why not we just change the water level and say that, yeah, I don't need so many memory. Okay? But what happens if the deallocation is in the middle? It's not at the end. The deallocation in the middle, can I shank? No, you cannot. You cannot shank. Why you cannot shank? If you shank the memory, then I put a cross here, okay? Why? Because as if you also deallocate this guy. You deallocate the last guy. What I want is the allocation of this memory, and you have tried, right? You create a series of malloc. You can choose whatever block to deallocate. But here, it's as if it's telling you that no, you cannot. You cannot just deallocate this guy. Because I changed the water level, I will destroy 2 blocks, not just 1. So what should you do? What should you do? Tell lies. Tell lies to the user that I have deallocated, but which is not. Understand what I mean? Yeah. I tell you that, yeah, I finished the allocation, but which is not. Now I show you the proof first. What's the lie? Okay, I will still make use of the malloc distance program. Okay. I use the malloc distance program. I go to the pointer 2. I set some special value. Okay. Best special value maybe is 12. The next guy is maybe 64. Okay. So I just come up with random numbers. You can also give me some random numbers if you want. Okay. So what I'm doing next, I will free pointer 2. Okay. Can I access them? Why I choose pointer 2? Because pointer 2 is sitting in the middle. Right? I deallocate someone in the middle, and I just have a claim that the memory manager, which is GNU-C library, the memory manager tells me that, oh, I should not deallocate it because I cannot change the whole area. That means what? That means here should print 12 and 64, not just this. I make it 2 and 3 after the free call. Ah. Crazy, yeah? So, let you to take a look at the program again. This is the program. CSCI. So, some warning because I never use pointer 1, pointer 2, and I. Okay, pointer 1, pointer 3, and I. Okay, but it's complete the compilation. So, what is the result? The result should be 0, 0. The free code is not here, okay? The free code reset my memory, okay? Yeah, but no, not a problem. Not a problem. The first three now is because it's not reset my memory to all zero. I don't care. I know that it is not being deallocated. I can use it back. See, I can use it back. That's horrible. It's what I'm telling you. I'm telling you that yeah, this is not something natural. Someone tell you in a class that yeah, it's deallocated. Don't touch it. I said touch it. Yeah, welcome playing around with it. It's still your memory. Right. Show you one thing more.
What happens if you
Huh? Free. Oh. Yeah. Good questions. That's why I don't try. I'm not sure. I'm not sure because it's based on implementation. When it's really shrink, it's totally based on the system. The system chooses not to shrink or choose to shrink. I cannot control. But I would predict that it won't shrink. Okay? Good questions. Let's try. I predict that it won't shrink. Because it's not necessary to shrink it. Okay, I believe it won't shrink. Alright, one more. Free. I should use regular expression to change it. Okay. Good. I predict that it won't change. Which won't change, huh? Trust me. Am I freeing the white guy? Yeah, free the right guy. Okay. Freeing the right guy. Go. Yeah, this is what I predict. Okay, I predict it won't change. It's totally based on the memory allocator who implemented. Why is implemented like that? Okay. So yeah, but forget about what I've just shown. I want a previous demonstration about the pointer tube. The pointer tube demonstration tells you that it really exists if you try to deallocate it and it becomes something like this. Now this is the real working behind the GNUC library, but this is an old version. Old version means this is more than 10 years ago. Okay. Nowadays it's just another tree-based allocation method. It's just something. I don't know whether you have heard of it. Some tree, okay, manage the number of nodes like this. Okay. First node is not tree like this. First node is two units. Second node is 4 units. Next node is also 2 to the power something. In order to make the allocation fewer and fewer. Okay. This is called skip list. Okay. Well, but it's just this way 10 more of your years ago. Okay. This way is first of all in the global area. So this global variable area, it's create a head node. Okay. Just like what you have learned from a linked list lecture, there's a head node. Okay. Where is a head node? It's just hiding per process. Okay. Per process have a global memory. Let's say you have a process, you have your head node. You have another process, just start, you have another head node. It's not something global to the entire system. So this head node, when you run, it's initially some null here, the size here, okay, no problem. But it's also hidden, usually in a data structure course, it's telling that, yeah, the head node and the list node, they usually have the same structure. Yeah, the head node and the list node is on the same structure, okay? So there are 2 fields. One field is pointer address, and other is the document. What is the size of the block? That is, let's say in this, okay? Is the document, the size which is 16 byte, okay? And one more field is document that what is the next? There's next pointer. Now let's illustrate how this linked list start, okay? First of all, the head node supposed to be of the same structure inside the global memory. The head node will start with a null pointer, it's pointing nowhere. But you say that, yeah, I want to deallocate someone in the middle. Let's say this gray block, okay, this gray block is in the middle. You cannot just change the group, the heap break, okay? So it will point to this guy, okay, and say that, yeah, this guy is a free block. And to make the list longer, okay, you will have the next pointer for the linked list. So the next pointer, now because you are the only free block, so you will point it down. Okay? So understand this part. This part is easy. We call it free list. Okay, initially, if you don't call free, the free list won't be generated. Okay, the free list is like this. Now, what happens if I do this? Okay, yeah, skipping call or skipping free call. You will generate a free list of something like this. Understand? I have tried. In a some years ago. Okay, those people just after hearing my experiment, they all got segmentation fault here. Okay, in the brain. So I've tried one experiment. The experiment is to create 1 billion malloc call. Okay, and I deallocate all the odd numbers and do an experiment and say that yeah, I claim that okay, there won't be any extra memory allocated if I deallocate all the odd numbers, no extra memory being allocated, and no memory is being free. Okay, I deallocate all the odd numbers just like here. Odd numbers 1, 3, 5. Okay, and then you generate the list. Okay, I can show it to you, but it's kind of hard. Okay, maybe you can try by yourself. You try to deallocate all things. Okay, and how can you prove that there's no extra allocation or deallocation? Just try to malloc one more block and compare the pointer. Then you will understand whether there is really deallocation happening, right? Okay, so this is the free call. Any question? The free call is just like a monster. It's just manage the memory by itself. And for the programmer, do you need to know this? Okay, I can make a difference. If you don't know about this, you will just like yourself yesterday complaining about the malloc. Yeah, why I have to use malloc? Yeah, this malloc sucks. Okay, it's always generates segmentation fault. No, after this lecture, you know that it's your fault. Okay, it's your fault. You say that you want 16 bytes. Please keep the playground within that 16 bytes. Don't use more. You can use less. No one complains. Okay, use more than that. You pay the price. Okay, this is the price that you have to pay, or you don't call any free. Okay, you don't call any free. There's no problem, right? Once you call free, the free list is generated, and while you generate the free list, there is a guarantee there. You have to guarantee that you don't pollute the memory in between, and to corrupt the memory in between is so easy. Previously, you see what I've done. I just use a pointer, start with it, treat it as an array, without any limit. Just try to write memory, let's say for 100 bytes. Then you can pollute the whole area. It's too easy, okay? And most of people will commit into this problem. They want 100 bytes of memory, okay? Or why? Because they have 25 integers, so they will do 25 times size of int, right? But they usually put down 25. Or 25 times size of char, I don't know why. Okay, then they will have freer memory than needed and try to pollute every guys after it. Okay, so after this lecture, you have to know who is your enemy. Of course, yourself. And free. Free is your memory, right? If you don't call free, no problem. Definitely no problem. Just the level 1 pollution. The level 1 pollution, you pollute the neighbors. Okay, level 2 pollution is you pollute the memory management block in between, and when you call free, boom, segmentation fault, and you don't even understand what the segmentation fault is. It just shows you that memory error. Let's take a look again at the memory error. The memory error already tell you something. Yeah, where is this? Hey, come on, baby. Here. See? Now I'm understanding the free list, then you understand what it's talking about. Invariant next size. The next free list block is something not known or embedded. Yeah, it's kind of related. Okay, once you corrupt memory next to you, you are actually writing false information inside the list here, and based on the false information, the memory allocator will make wrong choice. This is only level 1 knowledge over malloc and free. We will go to level 2 knowledge, the recycling of this free box. You understand what I mean? Let's say you want to deallocate memory, okay? Why people tell you to deallocate memory? You already know it, because in the Computer system, everything has a limit, right? Everything has a limit. You cannot cross such a limit. Let's say the limit is just 3 GB of available memory. Okay, you allocate 2 GB of malloc. Okay, I don't know how you allocate it. Maybe it's a scatter array. Okay, every time you just like me create 16 bytes. Okay, because you're doing your data structure assignment, data structure lecturer tell you that yeah, create a linked list nodes. Okay, create a list. Okay, you keep on allocating 2 GB memory. Now next generation of your assignment to tell you to free the memory randomly, and we create some of the block. Now there's a problem. Because you create this, it's not really freeing any memory. It's not really free memory. So what we expect that is, if you call the next level of malloc call, you may have a chance to recycle the memory. Now I will demonstrate to you. This demonstration is always lovely. Okay. So, tell me, what is the outcome? Maybe I have a pointer 4. Pointer 4. Pointer 4 is equal to malloc 16. Printf %d. Sorry. PTR 4 minus PTR 2. What would you say? First of all, pointer 2 is someone in between. Someone in between the series. 16 bytes. Now I allocate a new block after pointer 2 is free. And that new block is just so happen to be 16 bytes. Who votes? It is non-zero. So that means all agree it's 0, right? I don't have to run it. Yeah, someone's saying, yeah. Let's go, okay? GCC, okay? Yeah, because I have too many variables didn't use, okay? This program, run. Recycle. Yeah, it's being recycled. Now you should ask the next wave of question. Hey, how about I malloc for 16 bytes? Now let's recycle out of 17 or 15. Okay. Yeah, I will make you satisfied. 17. What do you think? Can you recycle? No, you cannot recycle. You cannot just steal 1 byte from anywhere. So you will have the distance being non-zero. Okay, GCC, cat. Now this is the program. Run. I don't believe it. 20. 我玩嘢喎。咦？哎呀 ，how about 24? Yeah, why is still the variable from the block? Let me binary search it. 20 is okay. How about 21? 21 should not be okay. Okay. But why 20 is okay? Interesting. 20. GCC, okay. Run. I have to look up the documentation. I bet, okay, the memory structure, okay, is not 8 byte in the new implementation. The old implementation is 8 byte. Now this is not 8 byte, 4 byte only. I guess. Okay, I have to look up. Okay. Okay. So one more stuff. One more stuff is, how about 1 byte? How about 1 byte? 1 byte should be okay, huh? 喂，玩嘢啊！ 1 byte. How about 10 byte? What? I cannot explain. What the? 15? Oh, what happened? Okay, I have to look up some code though. But yeah, it's just like random. Just someone suggests. Yeah, very dangerous, huh? Okay, so just give you some precaution before we stop this lecture. So the precaution is, well, now you understand why every time you call malloc, okay, you're being jailed inside this area. Now you know. You cannot go before it. You cannot go after this area because they are not owned by you. Okay, you cannot change anything. What's next? Next is, this is the question that in my mind while I was undergrad. Okay, I was undergrad, I always ask TAs, hey, why I have to return a memory, okay, and free with the same memory, okay, as long as the computer knows that, yeah, this piece of memory, all pointers or address are belonging to the same block. Why I cannot say that I return this, not return, supply this address to be called, why I cannot? Now I understand it because the memory is like this. If you say that you want to free this block, the GNUC library will do a subtraction and treat this purple area to be a false memory management unit. Okay, a false memory management structure. Okay, and you will get 72 points. Okay, it's not because this pointer, okay, is inside the area, and that's why now you understand that every time you call free, you have to supply this point. Okay, because it will do a subtraction and treat that block to be a management unit. Okay, so I still have something to go. Maybe next time. Okay, there's kind of a more. Okay, maybe I talk about this because this is easier. It is easier to look at it. Okay, so what is the problem here? You know, you can grow the heap. Do you ever try this program in your life? How many of you have tried? That means you're not naughty enough. Do you know what this program is doing? Huh? Is it too hard to understand? Oh, first of all, will this loop stop? There's a while loop, right? What kind of loop it is? Infinite loop, while what? Will it stop? If it stops, how? Okay, inside a while loop, while one loop, there's a break, right? So I'm challenging you one thing. Every people have learned about malloc, and every lecture, every book tell you one thing. You have to check the return value of malloc call. I guarantee that no one here check it. Yeah. How many of you will check the return value? Only you. Okay. Did you ever encounter any problem?
Not yet.
Not yet. Today you will. Let's go. Okay. Version 1, 2, 3. Okay, I have 3 versions. Okay. Version 1. I have some control here. Now, what is the control? First of all, I will let it run. Okay, and maybe it's hard for you to see. Someone don't understand this. I know. I changed it a bit. Okay. So it means pointer return now. Okay. Yes, return now. Then I will say p error malloc to let the system to print out its interpretable error so that you can read in a human format. Break. After the break, I will say, hey, look at me. Take a look on me. Using top. I will use top to show you whether the program has actually allocated that much memory. Or it won't. It just cannot touch the break call and it gets segmentation faults or even the machine reboots. Okay? So, in your mind, think, will I get this break? If get that break execute, that means that it's for the first time you receive null pointer is returned by malloc. If it's not, that means that it will keep allocating memory until when? Until I really use up the memory, maybe the machine will reboot. Let's do it. GCC minus, now take a look at the warning. Oh, minus, okay. No problem. Now, in your mind, give yourself a number. How many RAM I have in this machine, first of all? I have only less than 500 megabytes. Okay? So what will you expect? I will use up the memory if that program allocate more than 500 megabytes. Okay? Let's do it. This is strange. It just keep on malloc, allocate, and now this is the first time in your life that you see malloc return out. I guarantee you never see it. Okay, every people tell me the same thing. Okay, I didn't try. I didn't care about its return value. Now this tells you that you have to care about the return value. The return value gives you an error, cannot allocate memory. Now this is the first time you see cannot allocate memory, but something wrong. 3 GB. Something wrong. 3 GB. Now, I didn't stop the program. The program is still running. I can take a look at this PID. Okay, copy. Yeah, sorry, I forgot to see. Control Shift C I should press. Okay, Control Shift C. Okay, copy. Okay, open a new terminal. Okay, top minus P. That PID. Then you can see some statistics over this running program. What is this value? This value is what we call a virtual memory allocation. What is the value? Yeah, you can do a count. Is it really 3G? Close to 3G. 3 GB of memory allocation. Okay? So, and you can see how many percent of the memory is being used. Is it magical? I only have less than 500 megabytes, and you tell me that you use 2.6%. So that means it's still more than 100 megabytes, of course, right? But it's telling me that it's consuming 3 GB. Later, in part 2, we'll explain this problem. Okay? But what this program is telling you is something really magical. For the run, you will really have a while one loop malloc program, and it will stop executing. Now, if I change this program into this version, okay, because once I teach this, I have to teach you the next. If I don't teach you the next, okay, I having integrity problems, okay, because I'm telling you to do damage over the entire CHK. Okay, this program you are welcome to execute any machines, no damage at all. The next program I want to introduce to you is you should never execute in any program, any machines, never. MVM set PTR 1 meg. Then this will become a forbiddable program. I won't want. I don't want it now. Tomorrow I will train my EPC again, okay, and execute this program in front of the class, and you will understand what is the true meaning of out of memory. Okay, the previous execution is not out of memory. This is the true out of memory error. Okay, don't add this code, or you can change it in another way. Do you know what is MEM set? It's going through the pointer for 1 megabyte long and set every byte to 0. Oh, sorry, I swapped the parameter. Okay, it should be something like this. Okay, or you can do it like this. For I in the I equal to 0, I smaller than 1 mega, I plus plus, PTR I equal to 0. Just the same. Then this program will become a forbiddable program. You cannot run it. If you run it, you prepare Then first of all, you save everything, okay? Close all the browser, okay? And once it's run, I can guarantee you two observation. One observation is after running this program terminates. Your program is just like back into 1990 machines extremely slow. Or second effect is slicer reports. Okay, immediate reports. Okay, it will improve by itself. Okay, two possible errors. Okay, both of them are very damaging. Okay, next time I will bring my EPC to demonstrate it. If you are not patient enough, don't run this program in any public machines. Use your own machine to run it. Okay, if you're not patient enough. Okay, now time to stop. I will leave the content for tomorrow.
In terms of the use of carbon in assignment, that is in a scope.